Hi everyone! In this video we're going to discuss constitutional isomers. So constitutional isomers are compounds that have the same molecular formula but different spatial layout. So this would be kind of similar to, for instance, your hands. So your hands, you have a left one and a right one. And they are mirror images of each other. But if you tried to overlap your hands on top of each other, your thumbs will be on different sides, your forefingers will be on different sides. So they are different. And that's kind of similar here. So in this case, we might just have atoms in different arrangements. Okay, so let's look at the molecule C2H7N. Now, there's a few different ways that we could arrange these atoms. Now, as we've said before, hydrogens are usually on the edges of our Lewis structures because they can only make one bond. But carbon and nitrogen, they can make 4 or 3 bonds, respectively. So most likely the carbons and the nitrogen will be in the middle of this molecule. And there's a couple of different ways that we can draw that or connect them. So we could have carbon next to nitrogen, or maybe we have carbon next to nitrogen next to carbon. So these are our central atoms, and they're just arranged slightly differently. All right, so now let's draw the Lewis dot symbols for each. So remember, carbon has how many valence electrons? 4. So I'll just give each carbon 4 valence electrons. What about nitrogen? How many valence electrons does nitrogen have? 5. So I'll give the nitrogens 5 valence electrons. Okay. So now let's make some bonds between each of these central atoms. So we're just going to pair up these unpaired electrons. Okay, so these are our essentially our backbone for each molecule. So the only difference is nitrogen is on the end of the molecule on the left, and it's in the middle of the molecule on the right. Okay, so one thing that we have to do is place those 7 hydrogens around each molecule. And you'll notice if we just focus on the molecule on the left, there are 7 unpaired electrons. So we have 1, 2, 3, 4, 5, 6, 7 unpaired electrons and 7 hydrogens. So I'm going to put a hydrogen with its 1 valence electron next to each unpaired electron. Okay, so now we can start to make more covalent bonds. All right, and then nitrogen additionally has a lone pair on top. Although that could be on the side or the bottom. It doesn't really matter, but it does have a lone pair. Okay, so let's do the same thing for the other molecule because you'll notice we again have 7 unpaired electrons and we have to pair those up with our hydrogens. Okay, so we'll connect those unpaired electrons, we'll pair them up, make some covalent bonds. All right, so these are our 2 structures. So they do have different names. So the structure on the left is called ethylamine, and the structure on the right is called dimethylamine. And don't worry, we'll get into naming later on. So don't worry too much about the names at the moment. So if we look at these two Lewis structures, are all of the atoms happy? So in other words, or do each of the atoms have an octet of electrons? Yes. So each atom has an octet. Well, except for hydrogen, of course. Hydrogen only needs 2 electrons, right? Okay, so everyone's happy. Do any of the atoms have a formal charge? And feel free to pause the video if you want to double check. Nope. The formal charge on each atom in each molecule is 0. So both molecules are neutral. Okay. So now a couple more questions. Do you expect these two molecules to have the same physical properties? Now remember, physical properties are things like color, density, melting point, boiling point, etc. So do you expect these two molecules to have similar or the same physical properties? No, they actually have different physical properties. All right, so one physical property I mentioned was boiling points. So let's kind of think about boiling point. Now, when we boil something, we're breaking apart intermolecular forces between molecules. So there are 3 intermolecular forces, and we'll talk more about these later. So we have dispersion forces, we have dipole interactions, and then we have hydrogen bonding. Now, just a quick review of hydrogen bonding. A hydrogen bond is an interaction that occurs between a hydrogen and 2 electronegative atoms. So you might see a hydrogen bonded to fluorine, to oxygen, or to nitrogen. And one way to remember this is hold the phone. Hold the F-O-N. So one really good example of hydrogen bonding is with water. So if you have 2 water molecules, they're naturally going to orient themselves so that the electronegative oxygen is facing hydrogen, which is not very electronegative. But that hydrogen that's in between the 2 oxygens, so it's covalently bonded to one oxygen, and then it's attracted to the other oxygen, that hydrogen can form a hydrogen bond with the other water molecule's oxygen. So, so looking down below at our 2 molecules, you'll notice that we have 2 hydrogens bonded to nitrogen in ethylamine, and 1 hydrogen bonded to nitrogen in dimethylamine. So let's just highlight those. Okay, so how many hydrogen bonds could ethylamine make? So ethylamine has 2 hydrogens that could potentially form hydrogen bonds. And we could potentially have a hydrogen from another molecule that forms a hydrogen bond with that nitrogen up there, as long as it's bonded to fluorine, oxygen, or nitrogen. Okay, what about dimethylamine? How many hydrogen bonds could we make with dimethylamine? So we only have one hydrogen there, and we could again potentially make a hydrogen bond with that nitrogen as well, similar to ethylamine. Okay, so there is a difference there in the number of hydrogen bonds that we can make. So keeping that in mind, and also keeping in mind that hydrogen bonds are fairly strong compared to other intermolecular forces, which molecule do we expect to have the higher boiling point? So if we have more opportunities for hydrogen bonds to form, it's going to take more energy to break those apart, right? So we would expect ethylamine to have a larger boiling point because there are 3 potential opportunities for hydrogen bonds to occur. Okay, so if we actually look up the boiling point for ethylamine, it is about 20 degrees Celsius. And then the boiling point for dimethylamine is about 9 degrees Celsius. So these 2 molecules that have the same molecular formula have different layouts and they have different physical properties. So just keep in mind, constitutional isomers have very different physical properties. Okay, so let's kind of tie this into Lewis structures, which we talked about in the last video. So again, if you're trying to draw a Lewis structure for a molecule like the one on the last page, keep in mind that different elements can make different numbers of bonds. So we've already seen that carbon has 4 valence electrons, so carbon can make 4 bonds. So we call that tetravalent, and tetra stands for 4. We've also seen that nitrogen has 5 valence electrons, so it has 3 unpaired electrons and can make 3 bonds. So it is trivalent. We've also seen that oxygen has 6 valence electrons. 2 of those electrons are unpaired and can make bonds, so it is divalent. And hydrogen, we've seen, has 1 valence electron, so it can make 1 bond, so it is monovalent. But additionally, halogens, like chlorine, have 7 valence electrons with 1 unpaired electron, so it can also make only 1 bond. So it is also monovalent. So hydrogen and the halogens, they tend to sit on the edges of molecules. We call them terminal atoms. Now there are exceptions to that with chlorine, because chlorine can have an expanded octet in certain cases, but for the most part, it is a terminal atom. Carbon, nitrogen, and oxygen can exist in the middle of a molecule, but more often you'll see carbon and nitrogen in the middle versus oxygen. Now, if you want more practice drawing Lewis structures and predicting which atoms go in the middle and which are on the edges, I recommend trying the Skill Builder 1.1 exercise on page 3 of your textbook. And that is in the 3rd edition. It might be on a different page in the 2nd edition. All right, so now that we've talked about Lewis structures, we've been able to figure out how to draw two-dimensional structures. So as an example, let's draw the Lewis structure for CH4, which is called methane. All right, so which atom do we expect to go in the middle of this molecule? Carbon, because carbon can make the most bonds. And it's by itself, so that's another way. Okay, and carbon we saw has 4 valence electrons. And luckily enough, we have 4 hydrogens that we can pair up with those electrons. Okay, so I'm going to connect my dots, make some bonds. And as you get better at drawing Lewis structures, sometimes you can just skip drawing the dots and you'll just start drawing lines. It just takes practice. All right, so this is the two-dimensional drawing of methane. However, this does not accurately reflect the true structure of methane. So in this drawing, we're showing that there's a 90-degree angle between bonds. But in reality, that is not true. In reality, 2 of the hydrogens are in the plane of this paper, and then 1 hydrogen is kind of in the back. We show that with a dashed wedge, and another hydrogen is in the front, kind of coming out towards us, and we show that with a solid wedge, although my wedge looks more like a piece of wood or something. I'm not the best drawer. Okay, so all of these hydrogens are actually equally spaced around the carbon. So they're all 109.5 degrees apart. So all of those bonds are going to be equidistant from each other. Now, this brings us to Vesper Theory, which you might remember from Gen Chem. And Vesper is an acronym that stands for valence shell electron pair repulsion. So what that tells us is all of those hydrogens are treated as electron groups. And remember, electrons naturally want to get as far apart from each other as possible. So those hydrogens are trying to spread out enough that they each have their own space. And they each have equal space. Okay. So normally in class, I would give you this handout. It's a super useful review of Vesper theory and the shapes of molecules. But unfortunately, we can't see each other in class. However, I did post this on Canvas under study guides. So this handout comes from compoundchem.com, and this website has a lot of really cool graphics summarizing different topics in chemistry. So I encourage you to check it out just for, general interest. But let's step through Vesper theory and these different shapes. So up at the top, we have a key for how to read this chart. So in the middle is the shape. Oops. I was trying to highlight, not show you the next slide. So you'll see the shape of a molecule in the center. And then on the top of this circle, you'll see the name of the shape and the bond angle. And then on the bottom, you'll see the number of bonding pairs versus lone pairs. So the bonding pairs are atoms that the central atom is bonded to. Lone pairs are lone pairs of electrons. All right, so if we look at number 2 here, that's telling us that we have two groups attached to the central atom. Now, if we do have two groups attached to the central atom, that is a linear molecule, and the bond angle is 180 degrees. At the bottom, we can see that we have two bonding pairs and no lone pairs. Now, if we look at number 3, that's telling us that we have three groups overall that are bonded to the central atom. So in the first option here, we have three atoms bonded to the central atom. And this is a trigonal planar geometry with a bond angle of 120 degrees. So again, we have three bonding pairs. But one of those atoms could be a lone pair of electrons. So it just depends on the molecule you're looking at. But if you have two bonding pairs and one lone pair, that is a bent shape, or sometimes it's referred to as an angular shape. Now you'll notice that the degree or the bond angle there is a tiny bit less than for trigonal planar. And so this has to do with the fact that lone pairs actually push bonded atoms a little bit further away. So lone pairs take up a little more space than bonded atoms. All right. Now if we look at number 4 here, that means we have 4 different atoms or lone pairs bonded to the central atom. So in the first case, we have 4 atoms or bonded pairs attached to the central atom. So this would be a tetrahedral shape with a bond angle of 109.5 degrees. So that is our CH4 molecule that we just looked at. And there's other examples too. And then if we have 3 bonded pairs but 1 lone pair, then the name changes to trigonal pyramidal, and the bond angle decreases to 107 degrees because the lone pair at the top needs more room. So it's repelling those bonded atoms a little bit away or a little bit closer together. So one example of a trigonal pyramidal molecule is ammonia, or NH3. And then the last option here, we could have 2 bonding pairs and 2 lone pairs. And this would be another bent molecule. And sometimes to differentiate it from the first bent shape, we might call this bent tetrahedral, whereas the first one is bent trigonal planar. So you'll notice that for this bent tetrahedral shape, the bond angle is even smaller. It's 104.5 degrees, and that's due to the fact that there are 2 lone pairs that need even more space. So they're pushing those 2 bonded atoms even closer together. So a good example for this one is H2O. Okay, so you'll be happy to know that we are going to completely ignore 5 and 6. So 5 and 6, these are more so relevant in inorganic chemistry. So we're just going to ignore them for organic chemistry. Now, all those numbers we just went over is called the steric number. So that's the number of lone pairs plus the number of bonded atoms. Okay. So I think I'm going to stop here today and ask you to review Vesper theory and the shapes of molecules. I actually would also recommend kind of going through that chart at the top for how to find the shape of a Lewis structure. So for instance, first you would find the number of electrons that the central atom normally has. So same as we've been doing already. Then you add 1 electron for every atom that the central atom is bonded to. Then you add or subtract electrons to account for charges if the molecule is charged. Then you can divide the number arrived at by 2 to find the number of electron pairs. Then you subtract the number of atoms bonded to the central atom to find the number of lone pairs, and then you can arrange the electron pairs in the correct shape. So this is one option for figuring out the shape for a Lewis structure or for a molecule. But if you have a different way of figuring it out, that's no problem. This is just one recommended way to figure it out. Okay, so next time we're going to review orbitals. So we're going to kind of go back to quantum chemistry a little bit, and then we'll tie this back into Lewis structures and Vesper theory. But in the meantime, I encourage you to work on the problem of the day 1, which is on Canvas under modules, or you can use the link on the homepage calendar on Canvas. Just a quick hint for this problem of the day. Carbon typically does not like to have lone pairs of electrons. So just a hint. So again, we've gone over everything you need for Pod 1. It's not due until Sunday, September 27th, but I still encourage you to try this and kind of get it out of the way, right? Okay, so I will see you in the next video.